Okay, I want to come back to the concept of the instantaneous autocorrelation and how taking the Fourier transform of the instantaneous autocorrelation results in a time and frequency plot. So let's go back. This is from the previous lecture. This was a sinusoid correlated with itself. And so here we have time and here we have tau, which was the lag variable. So when we take the instantaneous autocorrelation, you can see that in time we get a sinusoid, in tau we get a sinusoid, but we also get cross terms, which are maybe better viewed in this other pattern. So here's the lag axis, here's the time axis, and then you can see that there are these off-axis terms that also looks sinusoidal. If we go along the diagonal, that looks sinusoidal as well. And that's because, as previously discussed, we have, when we take the cross-correlation product, we have these cross terms that are generated that result in that spurious information. So one of the ways to get rid of that is to use a filter, and use a filter in the time domain, a windowing kind of filter, before we take the Fourier transform. So it just depends on sort of the approach, but the first thing that I want to talk about is this idea of the Wigner-VA distribution. It's the most straightforward of what we call a Cohen's class of distributions, and basically it's determined by taking the FFT of the instantaneous autocorrelation over the lag dimension. So let's just go and look at what this looks like. So basically we have this instantaneous autocorrelation, and now what we're going to do is we're going to take the FFT either over the vertical dimension, so we're taking it over the tau dimension, and the result of that then, so basically we're doing an FFT here, 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 and so on, and the result of that then will be a function of frequency and time. So in general, Cohen's class of distributions. So what this is this equation looks kind of complicated, but basically the latter part of the equation is basically the Fourier transform, and it's the Fourier transform, basically taking the Fourier transform in two dimensions, nu and mu. So you've got the Fourier transform taken in two dimensions, I'm sorry, u and tau. So you've got the Fourier transform taken in two dimensions, and then you've got this other function here, this g of nu and t, or nu and tau, that's known as a kernel function. And what that does is that provides a two-dimensional filter onto the instantaneous autocorrelation. So basically, this kernel function goes in the integral, and it operates on the instantaneous autocorrelation function. And then once the kernel function has operated on the instantaneous autocorrelation function, the Fourier transform is taken. So the kernel function in Cohen's class of distributions operates directly on the instantaneous autocorrelation. And then, so that it's a time domain operation, pre-transform operation. So after that's done, then the Fourier transform is taken by accomplishing the rest of the integral. And so basically you could restate that as a two-dimensional convolution between the instantaneous autocorrelation and a two-dimensional filter. So the goal of the two-dimensional filter is to try and get rid of as many cross terms as possible. Now the Wigner-VA distribution, which is the one we just previously looked at, basically has a kernel function of 1. So it's simply the Fourier transform of the instantaneous autocorrelation, and so that's what results in all these unwieldy cross terms. But I think you can see that if before you took the Fourier transform, you could somehow apply a filter that would zero out some of these, or at least reduce the impact of some of these off-axis terms, that might be a really useful thing to do. So that's part of the role of this kernel function. Kernel functions are used for other things. They're used to transform nonlinear spaces, particularly in things like clustering algorithms where you need to reduce dimensionality, or sometimes you need to increase dimensionality. And so a kernel function can be used in those instances as well. But here it's primarily being used as a filter in T and tau. So as we said before, the Wigner-VA distribution does not have a filter, so the kernel function is equal to 1. And after we integrate by dv, the first variable, which is just the kernel function variable, the general equation reduces to the following, so a simple integral over d tau. And the discrete version can be written by taking the integral and replacing t with n and tau with k, going from n plus k to n minus k, adjusting the transform variable appropriately, and taking the summation as opposed to the integral. And then this factor of 2 shows up here because unlike this integral, which goes from minus infinity to infinity, this is a single-sided summation, so it goes from 1 to n. So basically, this is just the FFT of the instantaneous autocorrelation. So in this previous slide, this instantaneous autocorrelation is this Rxx of n and k is basically the discrete instantaneous autocorrelation function. The relationship between discrete and continuous variables is just like what it's found previously. Time t is n times capital T times s. The relationship between frequency and the harmonic number differs by a factor of 2 because in this case, in the continuous function, you're going by half lags, and in the discrete function, you're going by full point lags. So here's an example where we take that chirp signal that was used in the previous example, and basically we're going to plot we're going to apply the Wigner-Villay distribution and plot the instantaneous autocorrelation. So we're going to generate a chirp signal and then calculate the instantaneous autocorrelation. We'll then take the Fourier transform over the lags of the instantaneous autocorrelation. So when MATLAB's FFT routine is applied to a matrix, it takes the Fourier transform over the columns. So since the instantaneous autocorrelation places the lag values in the columns, then the FFT can be applied directly and we don't have to transpose the matrix. So here's the code for that. I won't go line by line through the code, but here's the code for that. WD is the Wigner-Villay distribution. You can see all it's really doing is taking the magnitude of the FFT of the autocorrelation. Here's the autocorrelation. So this is what that looks like, and you can see as we go along in time that the sinusoids get closer and closer together. You can see that as we go in lag, it's symmetrically distributed at a given time. So this would be like a single at a given time. This would be like a single sinusoid representing lags at different times. And then you can see we do get all of these diagonal direction sinusoidal distributions. So all of those cross terms are showing up, and you can see the increasing frequency as we increase in time. That's consistent with the chirp. Here is what the Wigner-Villay distribution looks like in a 3D plot in time and frequency. And so you can see it does not have a constant amplitude over time. Here is sort of like a contour plot of that. You can see it is pretty narrow, but its amplitude is not constant over time or frequency. So the Wigner-Villay distribution does have finite support in time and frequency, unlike the short-term Fourier transform. So finite support in time means distribution 0 before the signal starts and it's 0 after it ends. It doesn't contain frequencies above or below those in the input signal. It also has what we call favorable marginals and conditional moments. So the marginals relate the sum over time or frequency to the signal energy at that time or frequency. So we're having energies in the distribution that are similar or identical to those in the actual signal. So if we sum the Wigner-Villay distribution over frequency at a fixed time, we get a value equal to the energy at that point in time, which is what we want. We don't have extra energies showing up. It does contain non-existent energies due to cross products, as shown in the next slide. So due to these cross products, it's not necessarily zero when the signal is zero. While this distribution doesn't show energy outside the time frequency boundary of the signal, it may show non-existent energy where none exists. So it does not have strong finite support. So let's come and look at that. So here is an example of a signal that has two different sinusoids. So this is our 10 hertz and our 40 hertz signal that we looked at previously. And so if we look at this distribution, you can see the 10 hertz clearly shows up. You can see that it is the range of where there is energy present. You can see right here, it clearly begins at point 0.5, ends at 1, picks back up at 1 with your other frequency, ends at 1.5. So when we say finite support, the comparison of this and the spectrogram is that the spectrogram, if you recall, had all this energy out here past the presence of the signal and before. So that's what we mean when we say finite support. However, you notice that there is this cross-term region where we have these energies present that aren't actually real. So that's why the finite support is not strong. And they are well defined in both time and frequency. So you can see we do have a narrower frequency range here. But once again, we do show this large number of frequencies that are not present in our actual signal. So one of the ways to deal with these cross products is to develop an analytic signal. So an analytic signal has the same spectral characteristics as an original signal, except your redundant frequencies have been removed. The redundant frequencies are the negative frequencies. Now, in a real-world signal, when you're trying to represent, say, in the laboratory, you're trying to represent a sinusoidal function, and for whatever reason you do a mathematical transformation that puts that in the exponential e to the j omega t domain, what happens is, in order to get a true sine or cosine, you have to have both the e to the j omega t and the e to the minus j omega t according to Euler. So as we do all of these transforms, we've automatically generated positive and negative frequencies because that's the only way we can actually really represent real-world signals in the exponential domain. So basically what happens then is, because you have those positive and negative, you end up with all those cross terms because you have sort of this redundancy in your frequency. So what we can do is we can remove the negative cross terms. And basically that's done by taking the Hilbert transform of the original signal. So if our original signal is x sub n, the Hilbert transform basically says that the new variable is the original variable plus j times the Hilbert transform of f sub n. And what we're really doing is we're removing the frequencies above the sampling rate over 2 in the frequency domain, and we take the inverse transform. So what happens then is the signal itself is a complex number. And now, so the signal is no longer actually a real signal. It's a mathematical construct that we've created that makes our signal a complex number, so that when we take its Fourier transform, we get only positive frequency terms. That then enables us to do this manipulation without generating the cross products that we see in the signal that we've had. So for example, if you use MATLAB to take a Fourier transform and create a Fourier spectrum of a signal, you might get something that looks like this in MATLAB, where it's reflected around itself. And of course, as you know, MATLAB does this because MATLAB doesn't have a way to construct something for negative values of the index. So it takes the left-hand side of the function and it reflects it over on the higher frequency end. So given that MATLAB will do that, then basically the Hilbert routine takes the values below the sampling rate over 2, meaning you're not getting those reflected values that come from the negative part of the curve. There is a MATLAB Hilbert routine, and there's also a Hilbert routine that your textbook author has written. They're very similar. Now, there are a lot of different ways to implement a Hilbert transform. That's really beyond the scope of this course to go into great detail on how to implement a Hilbert transform. But basically, one way to do it is to implement it as a finite impulse response filter, similar to some of the ones discussed in Chapter 4, and the filter coefficients can be generated by this function. Um, a Hilbert transform filter needs to be perfect, obviously, an infinite number of coefficients, but in practice, if you take approximately 79 samples, that's typically a good approximation for a Hilbert transform. So a 79 order filter is typically what will work in this application. So here's what happens when we take an analytic signal and we do that to the instantaneous autocorrelation function. Here is what we would see as our normal instantaneous autocorrelation. When we take the analytic signal, it looks like this. So that doesn't necessarily mean a whole lot, except notice that now as you go along the diagonals, you no longer have that obvious sinusoidal variation that you have here. So you're not picking up those cross terms in the same way when you take the instantaneous autocorrelation on the analytic signal compared to the conventional chirp. So instantaneous autocorrelation and using the Hilbert transform is one way to visualize time and frequency space. Now there are other distributions that exist beyond the Wigner-Ville and the use of the Hilbert transform. There are other ways that you can get at this, and so in this case, the cross product reduction is accomplished by filtering the instantaneous autocorrelation before you take the FFT. So let me repeat that. Basically, we're going to reduce cross products by filtering the instantaneous autocorrelation function before we take the FFT. And we do this with just a distribution filter that's included in that integral in the Cohen's class of functions. So since the instantaneous autocorrelation is two-dimensional, the filters have also got to be two-dimensional. And they're defined by a determining function. So the determining function is given as this g of u and t, which is obtained from the kernel function g of v and t. It's basically the integration over the variable v. So there are several of these. One well-known one is the Choi-Williams, also referred to as an exponential distribution, and it has an exponential type kernel where alpha is some constant. So basically what this looks like is it kind of looks like a hat, like a Mexican hat, and it's got a peak in the middle. It's Gaussian shaped, but it's three-dimensional. So if you visualize rotating a Gaussian type shape, and so it's three-dimensional with u and tau being the axes. And basically what alpha does is it varies how rapidly the filter decays when you go off axis. So here is the Choi-Williams distribution function implemented in MATLAB. And if you plot it, it looks like this. And so you can visualize that if we have a time axis and a lag axis, that if we apply this, we're basically zeroing out an awful lot of the information that is on the diagonals. So here is our tau, here is our u. Notice all of those, if we apply this filter, all of those cross terms that were showing up off, kind of in the off diagonals, are going to be filtered away to zero by this filter, or at least it'll be partially effective at doing that. So let's apply this distribution as an example to the sinusoidal signal used in example 6.1. But instead of 10 and 40, let's make it 40 and 100 hertz. We're going to use the analytic signal and plot the distribution as a mesh plot. So the first thing we'll do is we'll use MATLAB's Hilbert to generate the analytic signal. We'll then construct an instantaneous autocorrelation using instantaneous autocorrelation, and then we'll filter that using Choi-Williams. And then we can do the Fourier transform after the convolution is done. So here's an example of that sequential sinusoidal signal with that Troy-Williams filter applied, and you can see that it's compared to one of the previous examples where we had little peaks here and here, and then a giant peak in the middle representing those cross terms. You can see we have far fewer. We don't have nearly the density of terms, and we don't have the amplitude of terms. So Troy-Williams did provide a moderate reduction in those cross product terms. There are lots of others. The Born-Jordan Cohen function is also implemented in your author's collection of algorithms. It's bjc.m. The determining function there is that g is 1 over tau plus 1, where tau is less than u. It's 0 otherwise. There's also a Born-Jordan, which is sine of u of t over u of t, so this is like the sink. You probably recognize that. So pretty much you can use whatever filter is of interest. Here is the sort of the distribution in u and t of those two functions. You can see this Born-Jordan Cohen is much peakier. This one is smoother, but you get these ripples in the diagonal region. So clearly this one is going to be better at smoothing, but it's not going to be quite as good at zeroing out the off-diagonal elements as, say, this function will be. So we can kind of visualize what that might do. And then there is the Rahachik-Margenot determining function, which essentially zeroes out all cross products in the instantaneous autocorrelation. So that's just another example of another type of function. So let's look at the application of some of these filters, some of these kernel functions to our signals, and I'll leave it to you to look at the code. It's pretty straightforward. So here is our 10 hertz or our 40 hertz and our 100 hertz signal with the BJT or the BJC, the Born-Jordan Cohen, applied on the right hand side. And so you can see the difference. You can see here was the Troy-Williams, and then you can see after instead of the Troy-Williams, if the BJC is applied, you can see the great reduction in those cross terms that were showing up in the center of that distribution. Here is the chirp signal. The BJC is applied over here on the right, and you can see the problem that it might not be an ideal thing for the chirp signal, because clearly you have some regions where the filter is acting in a way to zero out regions of the signal. So you really do have to just kind of look at your results, knowing what your signal is supposed to look like analytically, and just see what these filters are doing to that signal. Okay, and that pretty much concludes what we want to talk about as far as the application of kernel functions. So just to summarize in this chapter, what we've discussed is the use of transforms that incorporate both frequency and time in order to apply to signals that are non-stationary signals, which most biological signals are. We started out very immediately with the STFT, looking at the spectrogram. Then we saw some of the problems with that. We moved on to look at the transform of the instantaneous autocorrelation in the Wigner-Veillais distribution. We looked at how to apply kernel filters in order to reduce cross terms, and then we also looked at the use of analytic functions. So that's a lot of material that basically could comprise an entire course in itself, really compressed into this one module. But the main thing to get out of the module is that what we're really doing here is we are manipulating the appearance of the spectrogram of the signal so that we can get some information when we try to use that in an actual analysis.